in Python, we have more than just closures. We also have generators and generator coroutines. So if we take this formulation of this object with its inc and its dec in our typical class formulation, and we think, well, can we implement it slightly differently? Without using closures, we can implement this as a generator coroutine. And here we have a generator coroutine, which yields its current state and then takes in the operation that you want it to do. In this case, we can't really look at that state very easily. We can't retrieve the state without incrementing or decrementing it. But that's the same case on our other formulation as well. We don't have any get method that just looks at that state. We can only change it. And here, it is definitely the case that if we want to manipulate this object, we have to do .send with the message that's being sent in. And so shaving down that detail, making them look identical, would take additional contortions, very similar to the name tuple approach that we saw previously. But to a large degree, we can see that we have identical functionality, of course, if we fix our typo here. Now, if we dig a little bit under the covers, we know in the case of our object with the class keyword, we have this dictionary representing its internal state. But it's the case with the generator coroutine. If we dig into this, we can dig into the generator instances frame, and in that frames, it's f locals, it's local variables, and we can see an identical representation of that state. Now, in this case, this is actually a shadow of the underlying representation itself. That is to say, the actual fast locals of a Python function in its execution frame are stored in something more like a C array, and they're referenced directly by indexed access. This is to make it fast. It's not actually represented by a dictionary. And f locals is actually projecting that C array out into a dictionary because that's how we want to interact with it. And so, in truth, even though these look identical, under the covers, this representation is very, very similar to the closure representation with an array of each one of the cells and their contents. But whatever the case may be, I think I've proven the point that we have multiple distinct approaches to accomplish the same goal of object orientation without ever having to write that class keyword. Which brings us to an interesting question. Should we use object orientation? Should we write classes in Python? We can get away with not writing classes in Python. And of course, the approaches here are maybe a little bit clumsier or a little bit more obscure. But what does object orientation really gain us? And it is the case that we cannot avoid object orientation in Python dead stop, because the object model is the only way for us to extend the vocabulary of Python to implement the core vocabulary of Python. For example, if we have a Python list, we can iterate over that list. But if this isn't a list, but say a set, we can still iterate over it. If this isn't a set, but say an open reference to a file, we can still iterate on it. We just get the lines of the file instead. We can iterate over many different things because many different things provide this iterability interface. If we want to make our own custom data iterable, how do we do that? Well, this is where we are required to understand how some of the common structures that we see in Python turn into their mechanical forms and how those mechanical forms imply parts of the object model that you need to implement in order to make it work. For example, for iteration, we all know that iterating over something is the equivalent of calling the iter method and then calling the next method in an infinite loop, looking for a stop iteration which indicates whether you should break out of this loop. And so if we run this code, we get the exact same results as if we iterate over it manually. Now, it's probably the case that we would very rarely write this code. And in fact, this transformation is useful when we do a lot of work with generator coroutines. Sometimes we actually need to make use of this transformation to just interact with our generator coroutines the way we want. But for the most part, between you and me, I'd rather not write this if I could avoid it. I'd rather write this instead. But this gives me some insight into how I can make my own custom data iterable. Well, I need to implement that iter method so that I can respond to that iter top level function. And the thing that returns needs to implement a next method so it can respond to that top level next function. And here you can see I have some data represented in this class T that when you call iter on it, it gives you an iterator. This iterator is a reference to the original data plus some state, and this just gives you each subsequent element, assuming that that state is just an index that gets incremented in between next calls. If we want to implement the core vocabulary of Python, not just iterability, but other things like the context manager protocol, we either have to interact with that class keyword and those underscore methods or use a boilerplate elimination tool to do that. In other words, we know that context managers exist. In the context lib, we have, say, a null context that doesn't do anything, but just shows us what this syntax looks like. Here we have a context manager. If we wanted to write our own null context, well, we need to know that this thing turns into something that looks just about like this. We're going to create a context object here. Actually, we'll create a context manager first, and then we'll call on this context manager, enter. This will give us our context object, which is what you get when you do the as binding here. We'll try to do the body of this context manager with statement expression. And if we see an exception, we'll call on the context manager the exit method with 3 arguments, the exception value, the exception type, and the traceback. And so that's going to be a little bit tricky for me to pull out of this exception easily. But if we don't see an exception, we'll just pass 3 none values. And so if we wanted to implement this null context, well, it's pretty clear. It's even clearer than in the case of iteration. We just need to implement enter and exit. And as long as we implement these, then we are good to go with our context manager protocol. And you can see everything here works. We can even print out here that we're in enter. And we can print out here that we're in exit. And of course, these are printed twice because we have 2 instances of the context manager in this code. If it's the case that we don't want to interact with the object model, well, tough luck. This is the only way for us to extend it. However, Python is full of boilerplate elimination tools, and we can consider something like a context_lib.context manager, not only an adapter from one feature to another, but also a way for us to eliminate the somewhat clumsy or somewhat ugly boilerplate of this enter and exit method. We could instead write this as a generator with a yield in it. And here, of course, is the portion that would correspond to the enter. And here's the portion that would correspond to the exit. And behind the scenes, you can imagine all that's happening is Python is situating this structure into something that looks like this. Somebody somewhere has to write that enter and exit method. Doesn't have to be you, but it will be encountered if we want to extend the vocabulary. And so anything that we want to do to make use of that built-in Python vocabulary, attribute access, accessing something by get item, accessing something by open close parentheses, calling something, context manager protocol, arithmetic operations, all of these require interaction with the Python vocabulary and consequently almost always involve writing a class or using a boilerplate elimination tool to avoid having to write that directly.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.